Hello everyone, welcome to week 10 of the problem solving session for the course material and energy balances. So for this week, we will continue with few more types of energy balances, but here our focus will be uh, doing energy balances for reactive processes. So this week and the next week, we will focus on the broad topic of energy balance on reactive processes. A brief introduction about myself. I am Avchandra Paul. I'm a PhD student in the Department of Chemical Engineering, IIT Kanpur. I work in the area of tissue engineering and 3D bioprinting. If you'd like to know more about my work, you can go to my website and check it out. And if you have any queries related to the course, feel free to post it in the course portal. There is a Google group where you can post your queries, and also you can reach out to me at my email. So for the past 10 weeks, this is 10th week, we have been doing this session from 3 to 5 p.m. All the sessions that are held, they are all recorded and made available in my YouTube channel. The notes are also made available in your NPTEL course platform. So with this, I'd like to start with a small concept already discussed in the lectures, but a brief explanation about heat of reaction will help us to do some problems based on this concept. So by definition, the heat of reaction is basically the enthalpy change for a process in which the stoichiometric quantities of reactants at temperature T and pressure P, it undergoes complete reaction in a single reaction step to form products at the same temperature and pressure. That is the heat of reaction. It is defined with the unit kilojoule per mole. All right. And you can calculate the enthalpy change of the reaction from if you are given the heat of the reaction, and you can calculate the extent of the reaction from the reaction equation given. So from the reaction equation, you can calculate the extent of the reaction with this equation, where let's say for component A, if it's a reactant, A is a reactant. So and then for that, extent of the reaction will be number of moles of A involved in the reaction by the stoichiometric coefficient of A. That will give you the extent of the reaction. And for the same reaction, you are also given, if you are also given the heat of the reaction, then you can multiply these two and you can get the enthalpy change for a particular reaction. Heat of reaction for delta HR hat is basically negative for exothermic reactions, and it is positive for endothermic reactions. At low and moderate pressure, heat of the reaction is nearly independent of the pressure. So then we can write heat of the reaction as only as a function of temperature. The value of heat of the reaction, it depends on how the stoichiometric equation is written. So let's suppose there is an equation, reaction equation A plus B gives 2C. Okay, so let's say it has heat of the reaction delta HR. Okay, but if you write it as 2A plus 2B gives 4C, then your new heat of the reaction will become 2 into delta HR. So it depends on how the stoichiometric coefficients are written. Okay. Then since heat of the reaction is a state function, so it depends on the state of the reactant and the product, whether it is a gas or liquid or a solid. All right. And if you are given the heat of the reaction at a reference states of let's say 25 degrees Celsius and 1 atm, then this will be called the standard heat of the reaction, right? So let's understand those points in much more depth by solving some easy problems. This is question number 1 with 3 parts. So let's start with part A. It says that the standard heat of combustion of N-butane vapor is given by this. This is the equation. So we have to calculate the rate of enthalpy change. If 3000 moles of carbon dioxide is produced in this reaction, and the reactants or products are all at 25 degrees Celsius. Okay. So just now I said enthalpy change of the reaction is given by this equation delta H, right? Delta H is equals to extent of reaction into heat of the reaction. All right. So first we have to calculate the extent of the reaction. Since it is given as rate per second, so we'll calculate the rate of, like, the unit will be per unit, moles per second. All right. So extent of the reaction with terms of CO2, because for CO2 we are given the number of moles, that is 3000 mole per second, divided by absolute value of the stoichiometric coefficient. So for carbon dioxide, the stoichiometric coefficient is 4. So we will divide it by 4. So if you solve this, you should get 750 mole per second. And we are given at standard condition the extent of the reaction, the heat of the reaction, which is minus 2878. So enthalpy change will be then 750 mole per second into minus 2878 kilojoule per mole. So if you calculate it, you should get minus 2.2 to 10 to the power 6 kilojoule per second. Okay. This is part A done. Now part B. We have to calculate the standard heat of the reaction for this particular reaction equation. And then we have to also calculate what will be enthalpy change, rate of enthalpy change, for if 3000 moles of CO2 is produced. Now if you notice this chemical reaction and this reaction, you notice what's the difference? It is the stoichiometry. If you look at the reactions carefully, you will see that if this is reaction 1, this is reaction 2. Reaction 2 is basically twice of reaction 1. Reaction 1 is multiplied by 2 to get reaction 2. Since I already explained that heat of the reaction is depends on the stoichiometric quantities, So now the new standard heat of reaction will be twice of the previous one. So the previous one was minus 28.78. Minus 2878. This will give you minus 57 56 kilojoule per mole. Now using this using the new standard heat of reaction, we have to calculate the enthalpy change. But before that, the extent of the reaction is also changed now. Now it will be written as 3000 moles per second divided by the stoichiometric coefficient of CO2, which is now 8. Which is 375 mole per second. And then finally, the rate of change of enthalpy will become extent of the reaction that we just calculated into minus 5756 kilojoule per mole. It is the new standard heat of reaction. Will come out to be 2.2 10⁻⁶ kilojoule per second. If you notice carefully here, the standard heat of the reaction did change. The value of standard heat of the reaction, it did change, but the enthalpy change for the same number of moles of CO2 produced in both the cases is exactly equal. Okay. Now part C. Here, the heats of vaporization of N-butane and water at 25 degrees Celsius are given as 19.2 kilojoule per mole and 44 kilojoule per mole respectively. So you have to calculate what is the standard heat of reaction for this particular chemical reaction. If you notice, the butane state is now liquid, whereas initially it was gas in part A. And the state of water is now vapor, whereas initially it was liquid. So there is a phase change that took place. So because of that, the heat of the reaction will also change. Now what will be the new heat of the reaction here? It will be basically with the old one, which were this. If let's this consider 1, this is 3. So R3, R1. Okay. And if you notice, 5 moles of H2O in liquid state, it underwent vaporization to give again 5 moles of H2O in vapor. So 5 into heat of vaporization of water. And the reactant side, here only 1 mole of butane in gaseous state, it underwent, you say, heat is removed, right, to become liquid. So it is negative of negative C4H10. Here, one negative sign implies that it is a reactant, and another one implies that we have basically removed heat. And here we have added heat. So because of that, plus minus signs are included. So this will give us minus 2878 plus 5 into, here heat of vaporization of water is 44 kilojoule per mole, and for N-butane it is 19.2 kilojoule per mole. This will become minus 2638.8 kilojoule per mole. This is the new heat of the reaction, okay, for this reaction 3. Now with this we have to calculate change in rate of change in enthalpy. So extent of the reaction for CO2 will be 750 mole per second, and rate of change of enthalpy will be 750 mole per second into minus 2638.8 kilojoule per mole. It will be 750 minus 1.98 into 10 to the power 6 kilojoule per second. Right. So this is how we can calculate the rate of change of enthalpy if we are given the heat of the reaction, and if you are also given the equation, reaction equation, right? So in this way you can calculate. Now, apart from the heat of the reaction, you can also calculate the internal energy of reaction, which is basically, if you see the change in internal energy of the reaction at temperature T, it is the internal energy of the products minus internal energy of the reactants. If you assume that gas is ideal in behavior and the specific volumes of liquid and solid reactants and products, means all the reactants and products which are in liquid or solid state, their specific volumes are negligible compared to those of gas, then the internal energy, it can be related to the heat of reaction by this particular expression. Change in change in internal energy of the reaction is given by the heat of the reaction at temperature T minus RT. R is a universal gas constant into T, temperature of the reaction, temperature at which the reaction is conducted, into This is the summation of the stoichiometric coefficient of the gaseous products minus summation of the stoichiometric coefficient of the gaseous reactants. So all those reactants and products which are in liquid or solid state, they are basically neglected when you are going to calculate the internal change in internal energy of the reaction. So let's solve one problem using this concept. So this is the reaction expression given to you, and for this reaction, the standard heat of reaction is this. So you have to calculate the change in internal energy of this reaction. So first, let's calculate summation of the stoichiometric coefficients for products. Now you have to consider only those products which are in gaseous state. So this and this, 1 plus 1, 2. And summation of the stoichiometric coefficient which are in the reactant side, which are in gaseous state. It is this plus this, 1 plus 2, 3. So the final expression will be delta HR hat. This is the standard heat of the reaction minus RT into product minus reactant. If you put the values of the heat of the reaction, the universal gas constant, and the temperature. So here temperature is 25 degrees Celsius or 298 Kelvin. Alright. So this will become something like this, 8.314. Let me also write the units here along with the values. 8.314 joule per mole Kelvin, 298 Kelvin minus 1. Now since this is in kilojoule, so we also convert this into kilojoule. This will be divided by 1000, right? So what you would get, the final unit will be kilojoule per mole. When you calculate this, you should get minus 418.32 kilojoule per mole. So this was easy. Now let's solve a few more problems on the concept of heat of the reaction. Suppose delta H hat naught is minus 40 kilojoule per mole for the reaction 2A goes to B. What is the value of the ratio kilojoule per mole reacted per mole A reacted? So it's easy. It will be basically minus 40 kilojoule per mole. Now, stoichiometrically, there are 2 moles of A involved in this reaction. So 2 mole A, that means minus 20 kilojoule per mole of A. Now, is the reaction exothermic or endothermic? So since the value is negative, that means it is exothermic. If the reactants and products are at the same temperature, must the heat be added to or withdrawn from the reactor? We have to assume that the energy balance reduces to Q is equal to delta H. So what this means, since delta H is negative, Q is negative, so this means heat has been withdrawn from the reactor. Okay, is the answer. If the reactor is adiabatic, means there is no heat that can go in or come out from the reactor, then would the product leave at a higher temperature or a lower temperature? It will definitely leave at higher temperature. Okay. Set easy, right? Let's do another easy problem. You are given 2 reactions. Notice that in reaction 1 and in reaction 2, only difference is the state of C6H14. In reaction 1, the C6H14 is in liquid state. Now heat has been added to convert it to a gaseous state in the reaction 2. So what is the physical significance of the difference? And also because of this, there is difference in the heat of formation for both the reaction. For one reaction, it is minus 4163, and in second reaction, it is minus 4195. So what does this difference minus? What does this imply? What is this difference value that you would get? It would imply. So you should get around a difference of 32, right? Minus 32 kilojoule per mole. So what does this minus 32 kilojoule per mole imply? It means this is the heat of vaporization or heat removed to convert liquid state to gaseous state. Okay, that is what it means. This is another question. Now here you have to use the definition or the relation between change in internal energy of the reaction and heat of the reaction, relationship that we just saw a few slides ago. We have to use that relation in order to determine the value of delta U R hat, or the change in internal energy. This is the reaction. Let me write it again so that the reaction comes in one line. So first we have to calculate the stoichiometric coefficient of the gaseous products and the reactants. So stoichiometric coefficient of gaseous products, here only one product is in gaseous state. So it will be 1. What about in reactants? There are 2 substances which are in gaseous state. So 1 plus 2, 3. Okay. So net, so the change in the energy will be change in heat of reaction minus RT into product minus reactant. So it will be delta HR hat plus 2 into RT. Okay. So this is how you will write it. That is the formula you would get. Moving on, you are given to calculate, or you are asked to calculate the standard heat of the reaction for the following reaction of that uses 4 g/mole of ammonia. But for doing this, you would need to refer to the standard heats of formation. So there is actually a table that exists which gives the heat of formation HF and heat of combustion for a lot of compounds like acetic acid to, let's say, water. Like, it's a very long list, and you can see for which state you need. Like, let's say if I need for the liquid state of acetic acid, the heat of formation will be minus 40919, and the heat of combustion will be minus 871.69. So in this way, you can use this table to calculate the entire heat of the reaction. Okay, for the equation that is given here. Let's do that. From the table, okay, delta HF, standard heat of formation. It is basically at 25 degrees Celsius and 1 atm. For ammonia, oxygen, NO, and H2O. For ammonia, it is which state do we want? We want in gas, gas. All of these are in gaseous state. So ammonia in gaseous state has a heat of formation of minus 46.19. Here unit that I'm using is kilojoule per gram mole. That is very important, right, to consider. For oxygen, it is basically 0. It is not given here, but I found out. It is not given in this table, but I found out it is 0. What about NO? Nitric oxide, the gaseous state. It is minus minus plus 90.374. And for water in gaseous state, is minus 241.826. So these are the individual standard heats of formation for each of the compounds involved in this reaction. So now, in order to calculate standard heat of the reaction, change standard heat of the reaction will be your heat summation of heat of formation for products minus reactants. So in the product side, there is NO and H2O, and you have to also consider stoichiometric coefficient. So it will be 4 into 90 plus 374 plus 6 into minus 241.826. This is your products and reactants. It is 4 into minus 46.191 plus 5 into 0. Okay, so if you solve this, you should get so the final heat of the reaction for this expression for this reaction is minus 90 minus 904.696 will be in kilojoule per gram mole. Okay. Now moving on. We have to calculate standard heat of reaction for the following reaction from the heats of formation. Okay. We have to use a similar table in order to calculate it. So this is the table that we have. From the table, heat of or say 6H6 benzene in gaseous state, C2H2 in gaseous state. The heat of formation is C6H6, which is the benzene in gaseous state. It is plus 82.927. There again, the unit is kilojoule per gram mole. And for acetylene, C2H2 is in gaseous state. The heat of formation is plus 20 plus 226.75. Okay. Now I'll give you a minute and to calculate what will be the standard heat of reaction now. Hello.
Hi, yes.
Hi. So I was just doing some problems. All right. And
Hello.
hello. Do you want me to continue or should I go back? What do you want? I can. It's fine. We have time. Quickly explain some of the problems that I already explained.
No, you should continue. No,
Okay. Okay. So I was just taking a little break and I wanted to, you know, to um, for the people to attempt this particular problem. If you have done a similar problem previously, or maybe from the lectures, you can try doing this, the problem that is given on the screen. Okay. So, like the previous problem, here we have already taken data from the heat of formation and heat of combustion table, which I have written here. So it's quite easy to now calculate the standard heat of this reaction. So stoichiometric coefficient of acetylene is 3. 3 into the heat of formation of acetylene. This is the product side, minus for the reactant, it is 82.927. So you should get which I also got in my calculator, is 597.32 kilojoule per gram mole. So in this way, you can use the table to calculate the standard heat of the reaction. Now, the next question, in this particular question, we are going to use the Hess's law. So, very quickly, what does Hess's law state? It states that the general statement of Hess's law is, I'm directly reading from the book, it states if the stoichiometric equation for reaction 1 can be obtained by algebraic operations like addition, multiplication, subtraction, right? On the stoichiometric equations of for reaction 2, 3, like how many reactions you have, then the heat of reaction for this reaction 1, it can be obtained by performing similar operations on the heat of reactions of reaction 2, 3, 4. What does this mean? Like, let's say you have one reaction which is like this: A plus B gives 2C, and you are given another reaction which is B plus D gives 2E. Right, this is reaction 1, this is reaction 2. And if you like add these two, what you should get around A plus 2B plus D gives 2C plus 2E. So this is how you can like add. When you're adding, you're also adding the stoichiometric coefficient of the components which are present in both reaction 1 and 2. If this can be done, then let's say for reaction 1, the standard heat of the reaction is H1, standard heat of the reaction for H2. These two are known to you. And if you want to figure out the standard heat of the reaction of this new reaction that you got, then what you would do, you would just simply add the standard heat of the reactions of 1 and 2 in order to get the standard heat of the reaction for new reaction 3. This is what Hess's law states. Okay, so we'll use this concept to solve this particular problem. So you are given 3 reaction 1, 2, and 3, and for them the corresponding standard heat of reactions are given. We have to use Hess's law and the given heat of the reaction to determine standard heat of the reaction for reaction 4. Okay, so before we do that, let's observe carefully which all components are there in reaction 4 and how we can like get this reaction 4 from reaction 1, 2, and 3. So product is C2H6, this is 1, right? So it will go in the, so if reaction 4 we can get by subtracting first 1. Why we are subtracting? Because you will see in the later step, okay, when I'll write down in individually, or rather I should write it down individually here only. So this is reaction 4. First let's start with 2C. This carbon is present in the reactant side. Here in the reaction 2 also carbon is present on the reactant side. So if I multiply reaction 2 with 2 coefficient, should get 2C plus 2O2 plus 2CO2. So this 2 we are matching in the reactant side. Then H2 is present in reaction 3. So if we multiply 3 with reaction 3, you should get 3H2 plus 3 by 2 O2 plus 3H2O. Now if you add these two, then you would see, you would get the left hand side of your fourth reaction. 2C plus 3H2O. Here it is 7 by 2 O2 plus 2 CO2 plus 2 H2O. Okay. Now this is after adding this two. Now if you observe reaction 1, here it has 2 CO2. 2 CO2 is also there in your product side. 3 H2O is present. Yeah. 3 H2O is also present in your product side. So if you subtract reaction 1 here directly, from the new reaction that you got, like this, then what you would get? You would see these two will get cancelled, this two will get cancelled, and these two will get cancelled. So the final reaction would look something like this. Now here minus C2H6 means it will go in the product side. This is what the fourth equation is, right? This is what the fourth equation is. In order to reach to the fourth equation form, what we did, let me summarize. We multiplied 2 with reaction 2. Then we added this to 3 into reaction 3. Is reaction 3. And then we subtracted the entire expression of reaction 1. This is how we got expression 4. So this is what we have to do with the heat of the reactions as well. So the heat of the reaction for reaction 4 will be 2 into heat of reaction 2 is minus 393.5 plus 3 into heat of the reaction of reaction 3 minus 285.8 and minus 1559.8. Now if you solve this using a calculator, you should get it will be minus 84.6 kilojoule per mole. This is what you should get as your heat of the reaction for reaction 4. So this becomes very helpful in cases where you cannot perform this particular reaction experimentally, and thus you cannot determine the heat of the reaction experimentally. But if you are given, if you find out the heat of formations from the table itself, like this one, and you know how the expression goes, so from the known values of heat of formation, you can use Hess's law, apply it to get the heat of reaction for those reactions which maybe condition wise you cannot perform those reactions yourself. Okay, so this is another equation, another question based on Hess's law, very similar to the previous one. Here you are given the heats of reaction at 25 degrees Celsius and they are measured experimentally for the following set of reaction. Here's reaction 1, reaction 2. We have to use Hess's law to show that this is possible. So let's again see what we can do. How shall we get this reaction? Let's call it 3. So let's try first adding 2A plus B, that is reaction 1, with twice of reaction 2. So let me simplify this here only. Okay. If you add this to what you should get, no, adding won't help here. We have to do subtraction. Then this 2 will get cancelled. You would get B minus 2D. These two terms will get cancelled. And you would get minus 6E. And if we do a reverse, like bring 6C in the reactant side and send 2D the product side, this is the reaction 3 that we should get. So in order to get reaction 3, what we did, we subtracted twice of reaction 2 in order to get 3. This is 1, this is 2. We subtracted twice of reaction 2 from 1 in order to get 3. So we have to follow the same rule in order to get heat of reaction and heat of reaction for reaction 3. So it will be minus 1000 minus 2 into minus 2000. So what you would get 3000 kilojoule per mole. This is how we showed that. It's easy, right? Now here in this particular question, we have to compute the heat of reaction of the following reaction from standard heat of combustion data. I'll take a quick break of 2 minutes and then we'll continue with this question. I'm back. I had to quickly check on some experiment that is going on. So here, in this particular question, we have to calculate the standard heat of combustion. From the standard heat of combustion, so we will use this table correspondingly, just like we did for the previous ones. So let's first find out the heat of combustion or components C2H5OH, which is in liquid state, CH3COH, also in liquid state, C2H5O, CH3, and water. So first one is ethyl alcohol, C2H5OH, in liquid state. The heat of combustion is 1366.91. This column is heat of formation. This column is heat of combustion. I scanned it from the book, that's why it didn't come well, but let's see. Okay. So it will be minus 113 minus 133 66.91. The unit is kilojoule per mole per gram mole. Then for C3COH, it is basically acetic acid. So it is given here in liquid state. It is basically minus 871.69. The next component is ethyl acetate, C2H5OOCH5. Looks like this table does not have the value for ethyl acetate, but we can find it out. So I just quickly searched the internet and I found the heat of combustion of ethyl acetate is minus 2228, right? And for water, the heat of combustion is 0, right? If I like previously, standard heat of reaction will be given by product minus reactant, so minus 2228 plus 0, which I'm not writing, it is self-understood, minus this is with the reactor side. Here, stoichiometric coefficient for all the reactant and product is 1. Right? So if we solve this, we should get okay. So final answer is 10.6 kilojoule per gram mole. Right? This is what the heat of combustion, the heat of the reaction you would get from the heat of combustion data. And this is the last question for today's session. So the following heat of reactions are known from the experiments for the reactions below at 25 degrees Celsius in the standard thermodynamic state. Here the reactions, 6 reactions are given to us. So calculate the following. The standard heat of formation of propylene is C6H6 gas, C3H6 gas. And we have to also calculate the heat of combustion of propylene. So to start, what we'll do, when you're talking about the formation of propylene, that means the desired reaction is basically from carbon, which is in solid state, okay, and hydrogen in gaseous state, we should get propylene in gaseous state. Okay, this is the desired reaction. This is, and if you get the heat of reaction for this, this will give you the heat of formation. This is correspondingly equal to the heat of formation of propylene. So in order to get this expression, we have to use the reactions that is given to us. Basically, we have to apply Hess's law here. So let's start. If you look at reaction 1, it has C3H6. So let's start with C3H6. plus H2 gives C3H8. All right. If you add this reaction 2 is 1, which is C3H8 plus 5O2 gives 3CO2 plus 4H2O. If you add these, we'll see C3H6 come out, C3H8 and C3H8 cancels out, plus H2 plus 5O2 gives 3CO2 plus 4H2O. Okay. Now the story is not done yet. If you see now here, if you consider the states as well, let's write the states as well here. This is in gaseous state, gas, gas. It's in liquid. So if we take we have to remove this term and this term, right? These two will be there, and we have to also remove this term. This is the desired expression, right? So in order to do that, let's subtract 4, 3. So this is reaction 3. If we multiply it with 4 and then we subtract it from this expression, what you would get 4H2 gas plus 2O2. Here there is subtraction. Okay. Gives 4H2O in liquid state. So by this we will remove the water component altogether. What we are getting minus 3H2 means this will go in the reactant product side. 3H2 will be 3O2 here and 3CO2. What are the terms that we don't need? This one and this one. Let's find an expression with O2 and CO2 in it. So both of these expression has O2 and CO2. The difference is here carbon 1 in first expression, the carbon is in diamond state, and another expression, carbon is in graphite state. Okay. So if you look at the table, we can like take expression 6 here, all right? And for expression 6, what we can do, we can multiply this with 3. And subtract it. So 3 carbon is in graphite state, plus 3 CO2 plus 3 O2 gives 3 CO2. So upon subtraction, we will remove these two and these two components. And what we'll get? We get C3H6 gives 3H2 gas plus 3 carbon graphite. Now, this is what? This is like expression, reaction expression, which breaks down, right? Which breaks down propylene, right? So we have to reverse it. Plus 3H2 gives C3H6. So this is the desired expression. In order to get this desired expression, we had done some addition subtraction steps among the reactions. So you have to do that with the heat of reactions that is given here. So in the first step, what we did, we added the heat of formation of reaction 1 with reaction 2, which is giving us, if we add it, it is giving us the heat of formation of this expression that we got. So 1 and 2 minus 29.6 minus 530.6. So it is this minus 560.2 kilojoule per mole. Sorry, kilocalorie per gram mole. Now from this we have subtracted 4 into heat of reaction of expression reaction 3, which is minus 68.3. So this will give us what? Minus 560.2 plus 4 into 68.3 was minus 287, which is the heat of the reaction for this expression that we got. From this, we subtracted 3 into heat of the reaction of expression 6, which is minus 94.05. And it turned out to be 3 into 94.05. It is minus 4.85. This 4.85 is the heat of the reaction, which talks about breaking down propylene into carbon and hydrogen. So if we reverse it, the heat of the reaction expression heat of the reaction value will also change its sign. So the final heat of the reaction that you got will be plus 4.85 kilocalorie per gram mole. Okay, this is the final value. Similarly, we have to do it for part B as well. Now in part B, it is asking the heat of combustion of polypropylene, means it is going to react with oxygen. Okay. So how the final reaction would look like? Let's write the desired reaction. Here C3H6, it in gaseous state will react with oxygen in gaseous state to give CO2 and water. Now, if we do stoichiometric balance, carbon 3, (9/2). So this is how the balanced equation look like that we have to obtain from the given expressions. Let's start. Let's start with the first expression first. It is C3H6 in gaseous state plus H2O gives C3H8 in the gaseous state. Okay. So we have to get oxygen as well, but have to remove this component. So let's just subtract 2, all right, which is C3H8 gas plus 5O2 gives 3CO2 plus 4H2O. If we do a subtraction, no, if we do an addition, if we do addition, then these two C3H8 will get removed. And what we should get? We should get C3H6 gaseous state plus H2 gas plus 5O2 gas gives 3CO2 plus 4H2O. Okay. What are the terms that we don't need? We don't need this. And also we need to fix the coefficient of O2 and H2O. So we can maybe use the expression for formation of water if we just subtract it. Yeah, if we just subtract it, expression 3, which is H2 Here we are subtracting plus half O2 and H2O. You would get, these two will get cancelled. Yeah, should get C3H6 gas plus this is 5 minus half, that is 9/2 O2 gas. Here 3 CO2 plus 3 H2O liquid. That is the desired expression, right? Now if you follow these steps for calculating the heat of reaction for the final expression, this one, what you would get, first let's add up heat of reaction 1 plus heat of reaction 2. If we already did here, so it is minus 560.2 kilocalorie per gram mole. Now with this, we have to subtract minus 560.2 minus of heat of reaction of 3 minus 68.3. So this will give you the final heat of reaction this will be minus 491.9 kilocalorie per gram mole. Right? That's the answer. So with this, I hope you're able to understand from this session how to calculate the heat of the reactions in different scenarios, like using Hess's law or using the table of heat of combustion and formation for a list of compounds. Also, I have demonstrated how we can calculate the enthalpy change and the internal energy change for the reaction. In the next class, we will solve some energy balance problems, all right, which uses the fundamentals discussed here. So thank you all for listening to this video, watching this video, and I'll see you in the next one. Thank you.